Good morning. Got a little warm up here for you. And I have a question. If I'm trying to use a slightly different program that might give us a little bit more power and fun things like rainbow markers. But my question is, if I pause the sharing right now, do you guys still see the page with the numbers and everything on it? Yes, but you don't see it change now, right? It's still the same. Okay, that's really handy. Awesome. Good. Thank you. So go through, play with those, find those values. I don't know. No one's confirmed or argued with you, Alan, so I have no idea if you're right or not. But do you feel warmed up? That was the important part. Oh, you did. You sent it privately. Okay, well, that's good. That gives other people a chance. But I haven't seen anybody else's, so no confirmation or arguing. So, but I like that you sent it private, so you didn't give it away. Now, part of how long it's going to take really does depend on how one decides to go about finding that standard deviation, especially. So, if you're deciding that you really like finding standard deviation by hand and you're trying to plug all those numbers in and or trying to find all the subtractions, all the differences, squaring them, and adding them all up, that's going to take a while. If you brought up a nice version of Excel, then you could do it a lot faster. If you wanted to use your calculator, you can still do it quite a bit faster. So I'm not sure I'd recommend doing this by hand. So, well, I'm pretty sure I wouldn't. It's good to do these things by hand from time to time, but you know, having the technology there to speed it up for us is really handy. Oh, I'm sorry, your internet's bad at work. Well, let's see. Median 6, standard deviation. So that matches Alan's. I don't see your mean, but that matches what Alan got. So yeah, I don't want to spoil it either by hitting this last button. Well, let's see. Got a mean of 5.3. So type it over here. Oh, that went away. Mean of 5.3-ish, or 5 point, does it round up? Yep, 5.4. Standard deviation, we seem pretty agreed on 2.2. Standard deviation 2.2, we're using the sample standard deviation as opposed to the sigma for the population, so that's good. And there's a median down there somewhere, median of 6. Median of 6.
Nice.
Nice, yeah. Now, for the median, as we've looked at before, it is nice to put the data in order. The calculator doesn't require us to. Even finding it in Excel doesn't require us to, but it is nice in Excel to be able to just hit that sort and have it sort. But I do want to take a moment here because of what we're doing today and put those in order. So what is it? I gotta change the default size on this. So 2, and then there's a couple 3s, right? And a 4. Anybody write this in order? Can help me out? I'll figure it out. Is that all of them? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I missed one. What did I miss?
There's 3 6s.
Ah, there's 3 6s. Yes, indeed. Okay. So, one of the things we want to work on today is for our data set, whatever that data set happens to be, we want to be able to find that median. Ooh, that is thick. We want to be able to find that median. We'll see if that's better. Oh, that's better. Yeah. We want to be able to find that median, which we certainly can. The median was one of those 6s. And there were 11 data points. So 11 plus 1 divided by 2. 12 divided by 2 is 6. So it's the 6th data point. So 1, 2, 3, 4, 5, 6. So that 6th data point. That 1 is the one that is our median. But we want to be able to start talking about spread in this same type of way without dealing with the particular values, just how they're positioned. We want to start talking about spread. So the first way to talk about spread in terms of position is really one of the first ways we talk about spread at all, and that is to use the range. That angle's going to bug me. If this gets
Now that was part of the homework as well. So.
Oh yeah. See if that fixes the angle. So our range is generally pretty nice to find. It is the maximum value minus the minimum value. So in this case, it would be the 9 minus 2. So the range here is 7. So we got a nice range of 7. The bad thing about range is it doesn't tell us anything about what our values are. You could have a range of 7 going from, 1,000 to 1,007. That has a range of 7. But combined with the median, knowing that we have a median of 6 tells us that, okay, we're centered around 6, and a range of 7 means we're distributed away from that over 7 values. So often it's appreciated as a sense of spread because it is very easy to find. Take the biggest, take the smallest, subtract them, you have a range. It does have the disadvantage that it doesn't tell us much about how the data is spread out. So for example, if this 9 was instead a 19, that's going to change the spread to 17. Much larger range, sorry, change the range to 17, much larger range, but the data didn't change all that much. So range is pretty strongly affected by extreme values. Thus, it's not resistant. Thus, we tend to not like range too terribly much. But it is quick to find, simple to find, so we do like that. The preferred way to talk about spread in terms of position is with our quartiles. Hopefully you've done some reading with your quartiles. If not, do that reading. And they're called quartiles because there are 4 of them, and it breaks our data into quarters. It does write a lot smoother. That's nice. Breaks data into quarters. So we've already done some of that quartering. Used to that. Because we took this 6 and grabbing that 6 broke this data into 2 pieces, one lower portion and one upper portion. Do notice I'm excluding that 6 from those portions. So that broke us into 2 pieces. If I want to break into 4 pieces, well then each of these 2 pieces, the upper and lower, notice they're the same size, they have to be. Notice these 2 pieces, we could find a median for each of those pieces and break them into 2 more pieces. So for this first lower data set, the 2, 3, 3, 4, 5, it also has a median. What's its median?
3.
Try that. 3, and specifically that 3. What about the upper set? What's its median? Hovering over.
7.
Yep, that's 7. So that 3 and that 7, the median of those other quartiles, or sorry, the median of the upper set and the lower set, these 2 values are referred to as our quartiles. This is our first quartile. It's the first boundary. The median we often refer to as the second quartile because it is the second break. And this 7 is our third quartile. It's our third cut. Now that might seem a little strange. I said quartiles, it breaks us into quarters. You'll want to have 4 of them, and I've only got 3 here. But of course, 3 cuts break us into 1, 2, 3, 4 different pieces. And we often do label this first point here our 0th quartile. So Q0, often read just a Q naught from the Latin for 0. So we'll often refer to that first one as the 0th quartile, and that 9 at the very end, a 4th quartile. So those quartiles break our data essentially into a minimum, which again we often call Q0, our first quartile, our median, which we'll often call Q2, our third quartile, and our maximum, which again we'll often call Q4. So this summary of our data, the 2, 3, 6, 7, 9, this 5-number summary, it's a technical term by the way, if asked to give the 5-number summary of data. That 5-number summary gives us a nice sense of how the data is behaving. Gives us mins and maxes, so we can see our range. It also gives us an idea of how that data is spread out. The fact that we go from 2 to 3, that this 2 to 3 is this first quarter. So the lowest 25% of our data is between 2 and 3. The section of our data, the second quarter of our data, between 25% and 50% is between 3 and 6. Between 6 and 7 is the next 25% of our data. And notice that's pretty tight. Between 3 and 6, the middle, the 25 to 50% went from 3 to 6. So there was quite a distance between those, where the 6 to 7 is our 50% to 70% of our data. That 6 to 7 is really tight. So it tells us that, hey, our data tightened up here a lot because those are so close together when these were so far apart. So a lot of tight data here, some spread, tight data here, and then a little bit more spread, but not much here. We'll see this with bigger data sets. So the upper 25%, the high 25% of our data lives between 7 and 9. So it breaks our data up into these 5 pieces quite nicely. And that 5-number summary is a pretty common tool to want to nicely look at how our data is behaving. Now, we are going to see some examples where it's going to get a little bit stranger than that, but how does that seem as a starting place?
So if they were not an odd number,
Let me get to that.
then we'd be dealing in fractions.
No, well, sometimes. Let me deal with that. That's when things start to get a bit weird. So let me build up to that. Because you're right, I've rigged this one to be especially nice, no even numbers and stuff. I cheated. But we will look at examples like that, don't you worry.
Oh, I'm not worried.
Good. Before we do that, there is a visual display for data of this form that we want to get comfortable with. And that is, oh, that's handy. That is what's referred to as a box plot. So to make a box plot, we want our data with some sort of scale on it. So I'm going to put a scale on this. 1, 2, 3, 4. These should be evenly spaced. And contain at least all of our data. I'm going to put a couple more here just for reference. So we want a line that's got some scale on it. And what we're going to make is these 4 pieces. So that first quarter between the 0th quartile and the first quartile, that first section should go from 2 to 3. So I want a section here from 2 to 3. And then I want a section for our second quarter, going from our first quartile to our second quartile. That should go from 3 to 6. So from 3 to 6. Notice that's a box where this was just a line. We'll talk about that, the vocabulary for that in a second. Then our third quarter, going from our second quartile to our third quartile, go from 6 to 7. Again, oops. I like this tool, but it's going to take some learning. So from 6, oh, I gotta get it so it doesn't snap to the grid. So from 6 to 7. And then our last quarter is going to go from that 7 out to the 9. This again is referred to as a box plot because it's got a big box. But it is important that we have them listed in the way that they are. These lines on the end, they are technically referred to as the whiskers of the box plot. They are our outermost data. So we've got our fair, this is our upper 25%, that whisker, our lower 25% is this whisker, our middle 50% is everything in that box. Of that middle 50%, the lower part of the 50% is in the first box. The upper portion of the middle is in that second box. Notice visually, we can see here very dramatically how this third quarter of the data is much more tightly clustered, where this part of the data is much more spread out. It's one of the reasons we like box plots. It's very, here you've got to kind of look at the numbers and go, is it really that much more spread out? But when you look at the box plot, you can see this is very spread out. This is tightly clustered. That's tightly clustered. This is a little bit more spread out than the third quarter or the first quarter, but nowhere near as spread out as this second quarter. So box plots, very nice and visually impactful. They're very, very common to be used in a lot of applications. Sometimes you will see people add the mean into a box plot just because people love means. They're a very handy piece of information. So you'll see people sometimes go to that 5.4 and they'll put a diamond where the mean is. I don't know why a diamond, that's just what they use. So that would be our, oops, that should work. I wonder if that works. Oh, it does, awesome. So that's our X bar. That line is our second quartile, so it's our median. That line is our third quartile. This point is our max. We will have some issues with that in a little bit, but for right now, it is our max. That's our first quartile, and that's our min. Questions about that?
Why do they call them whiskers? Because they don't look like whiskers to me.
I don't know. Somebody probably liked cats. They look like little whiskers. If this was a little face, little whiskers coming off the face, I don't know. I got nothing.
If you pulled off all but one whisker on each side of the cat's nose, maybe.
I didn't say it was a healthy cat. I said it was.
Ah.
Yeah, I don't know. That's just what they call them. Generally, if you're asked to make a box plot, this diamond for the mean isn't really intended to be included, but you'll see it often enough that it is nice to know that that's what it's supposed to represent. And if you're asked to put the mean on it, that's how we put that mean on it. Questions about any of that before we look at some uglier numbers? Okay, I'm going to presume that means you guys are blissfully happy. The nice part about this, if you compare this to standard deviation, there's not a lot of calculations yet. It's just kind of organizing, so that's good. So those are our quartiles. When we want to talk about, before we look at another data set, When we talk about spread for position data, so spread by position, might only be one S in position. So when we start talking about spread, the value that we want to work with, instead of working with standard deviation when we're talking about position, what the tool we use is called interquartile range. I always like saying that, interquartile range. Rolls right off the tongue. But it often makes people nervous because interquartile range sounds like something terribly serious. But it is the range, so it's the difference between the spread of data of the inner quartiles. The inner quartiles are that Q1 and Q2, that Q1 and Q3, the 25th percentile and the 75th percentile. So that interquartile range is literally just that third quartile minus that first quartile. The range, the amount of distance between those two inner quartiles. So in this particular example, Q3 was 7, Q1 was 3, so our interquartile range is just 4. It tells us the amount of spread, instead of the amount of spread for all of our data, it tells us the amount of spread in that middle 50% of our data. So it's kind of similar to the idea of that, one standard deviation contained our middle 68%. The interquartile range contains our middle 50%. So again, for this data here, that interquartile range, the distance between the 3 and the 7 is 4. That way, again, if this 9 changed to a 19, it wouldn't affect our interquartile range at all. Heck, this could change to 119, and our interquartile range wouldn't change. It would change our overall range.
It would change the whisker, right?
It would sort of change the whisker. We'll get to that. Because this is so high, we want to have a tool for that, but we'll get there. So that interquartile range is not terribly affected, or not affected really at all, by extreme values, either high or low. If those extreme values go low enough that they start affecting that third quartile, then they're not extreme values anymore. They're just part of our data set. So that interquartile range is a resistant measure of spread. Where both standard deviation and range are non-resistant. They can be dramatically affected by extreme values. An A in spread. I can learn how to spell one of these days. So that interquartile range essentially is the position version of our standard deviation. So just like I wanted you guys to associate mean and standard deviation together, those two pieces of information together give us an idea of center and spread. You should similarly be associating median and interquartile range, because those two together give us a sense of center and spread based on position. So these two go together, these two go together.
Now, were you trying to use an arrow to point to something? Because all we're seeing is what you wrote. We're not actually seeing whenever you seem to be like identifying a specific spot.
You can't see this arrow move around?
No.
Oh. That's different. Cool. That's good to know. Thank you. So these go together and these go together. Can you see this, by the way, when I drop that down? Can you see those shapes?
Yes.
Okay. So it's kind of weird what you guys can see and can't see. Huh. Okay. Neat.
I mentioned it because that was the second time it seemed like you were trying to point something out, and neither time did I know what you were actually referring to until this last point.
Well, the other program, I could do that. You guys could see my pointer. So I could, just gesticulate towards things. But apparently this one you can't. That's interesting. Okay. I'll show you guys later some of the reasons why I want this, not just being able to type, but there's some other cool things that we can do that we'll see as we go along. Hopefully they'll be helpful. But before we look at a bigger data set with a little bit more issues going on, is there anything about this that's yet crazy?
I'm still trying to understand the relevance of it.
We'll look at some examples as we get for more data, but again, it's a way to talk about spread of data. So for example, if we had a different data set that was, say, 0, 1, 1, 1, 3, 1, 2, 3, 4, 5, 6, 18, 25, 32, 1, 2, 3, 35, and 50. This data set is quite a bit different. This data set is quite a bit different than this data set, right?
Agreed.
Now, they'd have the same median. This 6 is the median in both of them. This would have a much wider range. The range for this data would be 50. So that range would tell us it's a lot more spread out. But again, if we take this 9 and turn it into a 50, then this would still have a range. Well, it'd be 48, but still, it would still have a long range, but still be tightly clustered. Looking at this thing's interquartile range would be the difference between that 32 and this 1. 32 minus 1 is 31. That interquartile range mixed with this range tells us the middle 50% of this data is spread out by 31 units, very, very, very spread out, where this interquartile range was only 4, much more tightly clustered. So like standard deviation, its goal is to give us that sense of spread. This data set, if we didn't have the numbers and all you knew was that the median was 6 and the median of this data set was also 6, okay, those data sets might be very similar. This data set having an interquartile range of 4 means those numbers are all fairly closely clustered. This interquartile range of 31, okay, this data is really spread out by comparison.
But where would this apply in real life?
Let's say you've got a bunch of students. Let's say these students, these are their, I hate to say scores on a test, but why not? These are their scores on a test. So the test was, say, out of 50 points, so this was the max. It's common to want to know things like, okay, where did the middle 50% of my students score? Okay, the middle 50% of my students were in this big range versus some other class where the middle 50% might be more tightly clustered or the middle 50% might be in some other range. If you're trying to set power levels for engine output, okay, you know, where is, you know, the half of my data is going to be, or half of the engine output levels I have, half of the power outputs I have are going to be within these boundaries. So half the time I'll be more than this value, less than that value. It's just a way to talk about spread of data for whatever reason we might have.
No way to apply this to like horse racing or anything?
To what?
Horse racing. You know, something where I can make money off of it.
Sure. You know, how much money you made on particular days, you know, if your interquartile range is really wide, then there's a lot of variation in how much money you're making. You want that interquartile range to be tighter so that you're more consistent. Things like that.
Okay.
So let's look at both a slightly bigger data set and a little bit, oh, gives me time. That's neat. A bigger data set and a data set where we've got some more issues. So let's look at a why is that doing that? That doesn't matter. So let's look at a big data set. I'm going to put this data set in order just for our convenience. So let's say 5. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I'll make that a little bit bigger. So we got this data set. That data set is 14 data points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so it's 14. You can't see this eye moving around either, can you? You can see the eye, but you not the arrow? That's weird. Huh, okay. Good to know.
Yes.
Good to know. So in this data set, we want to be able to do the same thing. We want to be able to find the our quartiles. To start finding our quartiles, we first start by finding the median. So for that data set, take a moment and decide what the median is. I'll
25.
give you a minute to do that. I don't know what it is. See if anybody agrees. Anybody else? Alex, Tessa, Ali?
25.
Anybody want to back that up? Ali, I couldn't tell if you were saying something. Got 28. I love when you guys argue. Tessa or Alex? Audio isn't working. That happens. I'm glad mine's working. Tessa got 28. Alex, you want to weigh in? Maybe Alex would just be Z's. Well, let's find.
I
So
stand by my response.
So we had 14 data points. There is that little midpoint formula that they give you. Take the number of them, add 1 divided by 2. So that's going to be 15 divided by 2 is 7.5. So because it's 7.5, it's 7.5 because this was an even data set. That means it's going to be between the 7th and 8th data point. So if we go 1, 2, 3, 4, 5, 6, 7, and 8, that 7 and 8 end up being the 2 in the middle. Fair? So those 2 share that middle location. There's as many numbers above that, 1, 2, 3, 4, 5, 6, as is below that, 1, 2, 3, 4, 5, 6. So we can't have 2 values for the median. So we've got to take those 2 values and bring them together to give us 1 median. So the 22 plus 28 divided by 2, 22 plus 28 is 50 divided by 2 is 25. Alan, you said 25, right?
I did.
So our median is 25.
I used my calculator, by the way, everybody.
Aww. Does this logic make sense, though? Yes.
Not really, but I'll go with it.
Well, I don't want it to not really make sense. Process-wise?
Yeah, kind of.
Because if we picked the number 25, that 25 is essentially, its job is to be a break in the data set. A break such that half of the data is below it and the other half of the data is above it. Just like over here, that this 6 was supposed to break us into an upper half and a lower half. It's supposed to be that middle, that median. Over here, that 22 isn't in the middle exactly. That 28 isn't in the middle exactly. We need something in between there to act essentially as a boundary. So we pick a point that is equidistant from both 22 and 28. 25 is the same distance from 22 as it is from 28. And that 25 is going to form that boundary, breaking our list into a lower half and an upper half. So it will break us into this lower half of data. Notice that lower half of data includes the 22. And it's going to break us into an upper half of data, which notice includes the 28. So that's the job of that median, is to break us into those 2 pieces. There's a very important distinction here, that because that 25 wasn't an actual data point, because it was that just center between the 2, the 28 and the 22 are not left out of the lower section and the upper section. By contrast, in that first example, that 6, which is getting pretty messy, by the way, that 6 was excluded from both of the lists, because if we put the 6 in the lower list, this list would be longer. If we put the 6 in the upper list, then the upper list would be longer. Those lists need to be the same size. If we put the 6 in both of them, then we're double counting the 6. We don't want to double count it. So we label it as our quartile, and it doesn't form part of either the lower or the upper list. Again, by contrast, because this 25 is not an actual data point, we can go ahead and keep the 28 in the upper list and keep the 22 in the lower list. Fair?
Okay, so then the 12 and the 38 would be the splitting points of the other two.
Perfect. Oop, I did not mean to use that weird looking one. So the first quartile is going to be the median of this resulting list, which you're absolutely right, Alan, will be that 12. Again, if this was an even numbered list, we would do the same thing. If there were an even number of points, like say there was another one, so we'd have a 12 and we would be between the 12 and the 15, we would find the mean of those. So it's exactly the same. Find the median of the upper list. So that's a 12. The third quartile, remember the median is technically our second quartile. That third quartile, again, you're absolutely right, is that 38. So take a moment and use that information in our data set to find our two big things. Find the 5-number summary of that data. So 1, 2, 3, 4, 5. So find the 5-number summary. Oops. Make a box plot. And then find the interquartile range. I'll give you a couple minutes to do those 3 things. Alan, I don't like that 53. Good. Probably wait for me to fix that. Ooh, I don't like that. It's too small. If asked to give a 5-number summary, you really do want to label them when you're being nice and formal, but you can label them either min Q1, median Q through Q3 max, or feel free to label them Q0, Q1, Q2, Q3, and Q4 if you want. Either one is fine. So our minimum is that nice 5. Our Q1 is the 12. Our median, or Q2, the 25. Our Q3, 38. And yeah, our max, 56. Cool. If you've ever, and most of you probably have at one time or another, been assigned percentiles for things, like you take a test and you're told you're in the 90th percentile or the 30th percentile, or I don't know why I talk about having babies a lot in stats, but if you have a kid, they'll measure the head circumference and say the head circumference is in the 70th percentile for head circumferences. Essentially, that's what these are. They are our 25th percentile. Our 50th percentile is the median. Our Q3 is the 75th percentile. So you can think of these very much in terms of percentiles because that's what they are. So if thinking of them in terms of percentiles is helpful, then that's good. For our box plot, do make sure we have some good sense of scale here. So say 5, 10, 15, 20. I'm going to run out of space. I did not leave myself a lot of space for a box plot. Give myself more space. We do need the scale to be consistent because the size of the intervals is really what's important for our box plot, because it is a nice visual tool. The scale doesn't have to be terribly, I don't have to put in every little tick mark necessarily, but we do need to have an even scale. So our minimum is going to be 5, so our whisker is going to start at 5 and go to 12. Notice that really short whisker tells us this lower data was fairly tightly clustered, as it was. Then we're going to go our first box, our second quarter of data is going to go from 12 to 25. So it's going to go end there, 12 to 25. And then that 25 is going to go all the way out to 38. So that looks a little bit more spread out than the lower data. And then from the 38 to 56, a fairly long end whisker. And you'll often see people put little caps on the whiskers. They're not, I don't know if they're technically called caps. I call them caps. But so box plot. Questions about that? Yeah, Alan, I'm not sure what box. Okay, box 23. Yeah, those middle boxes should be touching each other. If we wanted to put the mean in there, the mean would probably be somewhere closer to the, closer towards the 30. This data is skewed out towards the high values. So these high values are probably going to pull that mean away from the 25 towards the right, because data looks a little bit right skewed. So if we wanted to find the mean and put the mean in as that little diamond, we could, but we weren't asked for it. We're not told it. We're not asked for it. So I don't see any reason to find it.
This would be skewed right?
Yep. Because these high values are more extreme than those low values, I would think the mean would be closer to 30 or so. So remember the skew follows the mean. So I think the mean would be a little bit higher. So the mean is going to be skewed to the right of 25. So I think our mean would be skewed right of that 25. If you found it on the calculator, you have that mean, right, Alan?
I do. Hold on.
Just for sake of argument, what is it?
26 point.
26.4. Okay, so very small amount of right skew. I expected a bit more. So it really is right up against that 25. So not much right skew, particularly in scale, off by 1.4 off of that median. So almost no skew at all, but it is a little tiny bit right.
Yeah, I was wondering that because if 25 is right in the center and 56 is almost a half of, 25 times 2.
Yep. But with these smaller, there are more numbers here in the 6s, and these are a little bit higher. So I thought these would pull it up more than it did, but it didn't.
Yeah, I was kind of thinking the same thing.
So what about the IQR, the interquartile range?
51.
51, that's our Q3 minus Q1. So our 38 minus the 12. That's not 51. It's 26.
Oh.
51 was the range.
Yes.
Yeah, if somebody asked what the overall range was, that's Q4 minus Q naught, or we usually say max minus min.
So inner implies the center of the two different quartiles.
Exactly. So the inner quartile range is that distance between the inner quartiles, the first and third. So where is that innermost 50% as opposed to where is everything?
12 to 38.
Right.
Gotcha.
Ali, absolutely. 26. Yep.
Good job, Allie.
Yay. Okay, questions about any of that before I make it worse?
Yeah, do you have to make it worse?
I do.
Of
I do.
course.
Yeah. So we do need to talk about what happens when some of the data is a little bit extreme. So I need another data set here, but a data set that's got some crazy going on. Not crazy, but some issues. So how about 07, 24, 26, 26, 28, 29, 31, 42, and 85. Okay, so why is this data a little weirder?
Well, 85 is quite a jump.
The 85 is quite a jump.
7 is definitely low.
So, yep, that eight, why is that working? So that 80, oh, wrong way. The 85 seems disproportionately high, and the 7 seems disproportionately low. The rest of this data is fairly clustered, but that 85 and that 7, you know, whether 77 is a big range or not, in comparison to how spread everything else at it is, that big jump to 7 and 85 is going to kind of cause some possible issues. So this brings in the question of what does it mean to be an outlier? Is that how you spell outlier?
LIAR, maybe.
L-I-E-R? No, I think that's right. Ali says it's right. I trust her. So
I do too. My spelling sucks.
So what does it mean to be an outlier? Outlier is actually a technical term. We might think of it as, well, if we're more than 3 standard deviations from the mean, that's supposed to be outside of almost all. And most outliers are outside of 3 standard deviations from the mean, but that's not necessarily true. Being an outlier is really a position argument. So it's based on our quartiles and that interquartile range. So if we wanted to determine the 5-number summary, interquartile range, and make a box plot for all of this, we're going to have to deal with this issue of outliers. So first things first, we need that median. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9 data points. That's handy. So that 28. And then we need the Q1 and the Q3.
Q1 would be 25. Q3 is 36.5.
So for this lower data set, it's going to be between the 24 and 26. So I'll absolutely agree with the 25. For this upper data set, again, notice I'm excluding the 28 because it was a singular data point. It's going to be between the 31 and the 42. What's between 31 and 42? It's what, 73, so 36.5?
Yep.
Cool. Before we go on with that, questions where any of those came from?
My calculator.
Your calculator. Do you be practicing without that calculator, Alan? We want to make sure the logic of where they're coming from is sinking in. I know, but I like the calculator. The calculator is a good tool, but we want to not become overly dependent on it. Is that fair, Alan?
No.
No, it'll help you in the long run. I only say that because I care.
I do get the gist of it. So the calculator's not hurting it, just making it easier. But yeah, like on the second Q or the Q3, that would have been the difficult find.
Yeah. Just make sure as you practice a little bit of both.
Gotcha.
So what's our interquartile range?
Looks like about 25.5.
Anybody want to argue with Alan? I love when you guys argue with Alan. Yeah, it's our Q3 minus Q1.
Oh, oops.
So the 36.5 minus the 25. So, yep, 11.5. I am starting to angle.
Way to go, Allie.
Yay. So that interquartile range is 11.5. So how we determine whether something is an outlier or not, it is in many ways a little bit of a strange calculation. And I can't actually tell you exactly why this is what they use. This is just kind of the default that the stats community came to over time, that what are we going to call or consider to be outlying data. But to be an outlier, you have to be either bigger than the third quartile. So you'd have to be bigger than 36.5 plus 1.5 times the interquartile range. So we'll take that interquartile range, multiply by 1/2. That's going to push out from that third quartile and give us a boundary for where we're going to call everything past that boundary an outlier. So our Q3 here was the 36.5. If we add 1.5 times our interquartile range is 11.5. So 36.5 plus, what is that? 6.75. So is that 18.25? You guys have calculators? Back me up. Or tell me I'm wrong. I love being told I'm wrong. It's how I learn. Allie, a little yeah. So then if we add these together, we're going to get, what, 54.75?
1.5 times 11.5 is 17.25.
17. Oh, I added it twice. Thank you. So that's going to be 53?
53.75.
Okay, 53.75. So that means 53.75 is our boundary. Anything outside of that, anything further out than 53.75 is going to be labeled an outlier. So is this 85 an outlier?
It's a stinking outlier.
It's a fairly good, strong outlier. It's more than 1.5 times the interquartile range from Q3, from the outer quartile.
And same deal with
All I heard was same deal, but you probably mean same deal for lower. And yeah,
with the 7.
we use the Q1 instead. Instead of measuring from the third quartile, we measure back from the first quartile. So that first quartile minus 1.5 times the interquartile range. So it's going to be that lower quartile, the 25, minus 1.5 times the 11.5. So you'll have to help me with this subtraction. So 25 minus 17.25 is, 7.75? Is that right?
Give me just a second. $7.75.
Yay, 7.75. So anything that's lower than 7.75 would also be an outlier. So what about this 7? Is this 7 an outlier?
Yes, but just barely.
But just barely. I like that. So we need to know that because when we start doing things like our 5-number summary and our box plot, that gets taken into account. So when we talk about our minimum, our Q1, our median, our Q3, and our maximum, it's going to seem uncomfortable, but this minimum value should always be the minimum non-outlier in your data set. We're not excluding the 7 and the 85 from our data. They're not being thrown away. But when we list the minimum, we want to express that this minimum is our smallest, quote unquote, normal data. So we wouldn't use the 7 as our minimum because it's an outlier. What would we use instead?
The 20.
The 24. Then our Q1 is still the 25. That median is still the 28. The Q3, still the 36.5. And again, that maximum will be the maximum non-outlier.
42.
So it'll be the 42.
That's a lot to remember just to get rid of those stupid outliers.
I know, but outliers cause trouble. If we told somebody instead that our maximum value was 85, well, let me draw the box plot first. You'll see what happens if we didn't do this, what the consequence is. Let's jump right to that, drawing that box plot to get that sense of why this is considered important.
It's just a longer whisker is all, isn't it?
No, it is not a longer whisker. But we'll talk about that. I'll show you. 10, 20, 30, 40, 50, 60, 70, 80, 90. Okay, so I want to work from the inside out. We'll start at that 28. So that 28, that's our median. Our box goes back from 28 to 25. So really small box there comparatively. The Q3 goes up to 36.5, so about there. Then our whisker. Our whisker goes from a Q1 to the minimum non-outlier. So it only goes from 25 to 24. Our upper whisker does the same thing, goes from Q3 to that max of 42. Now, we do want the 7 and the 85 on this graph, but we don't want them in the whisker. We do want to label them, though, so they're just, usually they use little stars or X's or sometimes just dots. So a little dot there at 7 and a little dot way out here at 85. Or again, some people use a star or an asterisk. Now, why do we do that? If we look at this data, this lower section of data doesn't go all the way from 29 to 85. Well, it kind of does, but our data isn't spread out evenly in that range. If we drew the whisker going all the way from there to there, that would communicate to our audience that our upper 25% data is, or the upper 25% of our data is distributed throughout this range, and it's really not. It's only really distributed through this little whisker. Oh, and there's a singular point way out here. We want to display that distinction. I don't want people to think this lowest 25% goes all the way kind of evenly and there's a whole bunch of stuff between 7 and 24, because there's not. There's a couple of little data points right down here and then empty space until that 7. So it really does change how the data appears to have those little short whiskers as opposed to having the whisker go all the way out and convince people visually of something that's not happening. Does that make sense, Alan?
Yeah, it just kind of seems almost fictitious because we do have those points. It's almost like we're neglecting all of the information.
Well, and that is why we want to make sure that they're included here. So on our box plot especially, we do want to make sure they're included. And it's one of those things. It's kind of like it's as important for us to know where data is as it is for us to know where data is not. So I don't want to make people think there's data in between here. So I don't want to show it to them as if it is. But you're right, I don't want to leave that point out completely, so I don't want to ignore it. So we want to have it there. Like, and often if you list these, you're particularly right about the 5-number summary. The 5-number summary, if that's all you were looking at, you wouldn't even know the 7 and 85 exist. So you'll often see it, okay, now it looks funny. You'll often see it accompanied by a list of, okay, here are my outliers, just so people know they exist. But I don't want people to think my data is fairly evenly distributed between 7 and 85, because that's not what's happening here. The data is really distributed between 24 and 42 with a weird point on either end.
So those are like
Exceptional data. And oftentimes people will decide, well, maybe I should take them out of my data set completely because they're weird things that happen. I don't want to be part of my average. Some people will want to include them. So it partially just kind of highlights them and says, hey, look, these data points were weird. Let's look at them. Let's make sure we are considering them in the way we want to.
How much is this going to play into our homework?
Oh, you'll be asked things like, is this an outlier? Does this data set contain any outliers? You'll certainly be asked for 5-number summaries and need to exclude them if you need to. You'll certainly be asked to make things like box plots. So yes, absolutely, you'll need to know.
Okay.
Allie, I'm going to have to look at that because your homework should not be saying use 2 standard deviations for outliers. If it is, I'm going to yell at it. Question 4, I'll look at it because that's not technical. The 2 standard deviations should be unusual, not outlier. So I might have to yell at the, it is an open source program. So, we try to fix them when we find things like that. So it is good to point things like that out. Thank you. All right, so go play with these, have fun with it. If you have questions about it, let me know.
Since Allie found a mistake, shouldn't that mean we don't have to do our homework?
You never have to do your homework, Alan. You don't have to do your homework. You don't have to come to class. You are not required to grow as a person in any way.
Well, I don't think I'll be coming to class, but I will meet you here online every morning.
That would be good. I enjoy that. I enjoy having you here. So keep doing that.
So also, did you get my message about my late thingamajigabobber?
I don't remember. Was it on my open math? Or was it?
Yeah, my late pass there.
Oh, yes, I did. I fixed those.
Okay, and were we supposed to also, in addition to 3.2, are we also supposed to be able to have access to 3.1?
No.
Okay. Bummer, but okay.
Okay. Anything else? You guys good?
Allie has a message.
Allie has a question. Also this week I saw a test 1 review. Does that mean next week we're having a test? Or how is that working? Yes, we'll talk tomorrow about when we're doing that test and how we're doing that. Cool.
Bye, everybody.
But have a wonderful day. Hi, Kim.
Hello.
How are you doing?
I'm doing good.
Good.
I still never got to go back and do the second and third part of the lab 1, but I'm not worried about it.
Well, and we can go back and figure out why. I still don't know what that was about. I still don't know what the issue was.
I just